Thanks very much. It's great to be here. I'm Naomi Nickerson, and I'm going to give you a bit of an update on some of the things that have been going on in quantum architecture at PsiQuantum. So some of you might have heard Pete Shadbolt talking yesterday, a lot more focused on the hardware. So today I want to look at the other side of that and how we can start to design architectures for fault-tolerant quantum computing with photons. So at PsiQuantum, we're building a hardware based on photonic qubits. And I think people at PsiQuantum like to say, photons are different. There's many ways in which this way of encoding quantum information behaves and acts very differently to building qubits with matter. And there's many ways in which this is true. So the photons themselves are not intrinsically qubits. They're traveling at the speed of light. There's trade-offs between space and time that you can make use of. There's kind of intrinsically no quantum crosstalk because the photons don't interact. The list really goes on. And if anyone here has seen a talk that I've given before, or maybe one of my colleagues at PsiQuantum, you'll probably have heard some version of this message. And we say a lot of things like, well, we have all this non-local connectivity with photons because of optical fiber. Surely there's some way that we can make use of that to our advantage in making the architecture more efficient, or the errors, the way they happen in photons dominated by optical loss, that's also very different. Like, isn't there a way we can make use of that to improve error correction? And so today I want to give you a bit of an overview of that architecture, but also give a few answers to some of these questions that we've been kind of thinking about for a while, which is, yes, in fact, with non-local connectivity, we can now show ways that you can use that in the way you compile and design architecture to really reduce the runtime of algorithms. And also looking at error correction and how much loss we can tolerate, there really are ways that you can kind of push things much further by making use of the specific ways that errors happen with photons. So give you a look at some kind of new results in these areas. But first, to go back to the architecture and just to talk about the way that PsiQuantum has approached the architecture from the very beginning has been to look at fault-tolerant quantum computing. And that's because, as far as anyone knows today, it's going to take billions of gates, millions of physical qubits to get to the point where we can really harness the power of quantum computing. And that demands extremely low error rates. And so we're really looking at algorithms and architectures that are operating in this fault-tolerant regime. And there's many ways in which that's really fundamentally different approaches. And of course, scale is one of them. So to get to fault tolerance, you need a very large number of qubits, a very big quantum system. But actually, the differences go much deeper than that into the heart of the way the architecture is set up. So in a NISQ setting, you tend to think about unitary evolution of qubits. So lots of gates that operate in sequence, and then only at the end of the circuit do you perform measurement. In the fault-tolerant setting, everything is about measurement. It's measurement all the way through, and you're just constantly making projective measurements on your qubits. And so, really the operations themselves look very different. And then if you look at algorithms and what is easy and hard, it's almost a complete inversion between these two settings. So in the NISQ case, it's single qubit rotations that are the cleaner, easier operation, while entanglement is hard and tends to be more noisy. But when you're in the error-corrected case, it's exactly the opposite way around. So doing small angle rotations becomes really hard, really expensive, but entanglement, even large multi-qubit entangling operations, is relatively easy. So just with that as the premise, this is why for designing architectures for fault tolerance, we really need to start incorporating that into the very heart of the way everything is designed. And so we've spent the last few years really digging into this architecture and looking at it all the way through the stack, from the point where you have a quantum algorithm and how you can compile that through all these different layers to ultimately get to hardware instructions. So this stack probably looks pretty familiar, and it should, because actually the story is very similar for a lot of it. A lot of the way that you look at compiling to fault tolerance is the same across different platforms. But when you get down to the lower levels, much closer to the hardware, that's where the photonics really comes in. And so what I'm hoping to do now is just give you a bit of an overview of what goes into that stack, how the pieces fit together, just so you can get a sense of what a photonic quantum computer looks like. and then go on to look at some of these new results that are starting to move beyond what is there, just the kind of baseline photonic architecture. So I'm going to start at the top. You can see the sidebar is kind of guiding you through what's going on through this photonic stack. And the first step is, we want to take ultimately a quantum circuit and be able to map it all the way down into instructions that are going to run on this photonic hardware. And so our starting point is to take some arbitrary algorithm, some circuit, and turn it into an instruction set that's native for fault tolerance. So there's restrictions that come into play when you're working with fault-tolerant qubits. And there are different ways this can be set up, but the way we're choosing, kind of pretty common approach, is to look at this architecture of Pauli product measurements. So this is really an instruction set architecture. It tells you what gates we're able to run on these fault-tolerant qubits. And in this setting, all of our gates are getting compiled into these multi-qubit rotations happening on sets of your logical qubits. And by applying a certain angle to those gates, we're able to implement kind of a varied set of gates. When that angle is pi/8, this is basically equivalent to a T gate. And so the thing to note about this way of compiling is that all of the Cliffords, all of the Pauli operations at the end, all just absorbed into this sequence of gates. So everything in the end just looks like a sequence of these multi-qubit Paulis. So this is the top layer. Then we want to move on to looking at how we actually implement those Pauli product measurements in hardware. And that's going to depend on what is the connectivity and layout of your logical qubits, and maybe what kind of specialized functions you have in the architecture at that level. And so as a baseline, we're going to take this linear register architecture. So this is work from Daniel Litinsky from a few years ago, where we have a series of memory qubits. We have local connectivity, sort of pairwise connectivity between the qubits in that architecture, a linear ancilla that's allowing us to interact between the different qubits. So that's what's enabling the computation. And then we have one specialized block, which is the distillation block, and that's allowing us to create magic states and insert them into this machine so we can do our T gates, our non-Clifford operations. So zooming in a bit further, we now need to get to error correction. So we want to be able to build those logical qubits in a way that's protected from error. And so here we're choosing to work with surface codes and a patch-based encoding. So very familiar approach where the logical information is encoded in the topologically non-trivial states of this patch. And we take a kind of series of these things, all our logical qubits, and we can perform logic by making operations on these things over time to build up these circuits that have this topological structure. So this picture on the right kind of showing how you can build up this shapes over time. And it's these topological circuits which are really what is running the algorithms, running a series of logical gates. But to make these things tractable, right, we need to turn it into an actual instruction set, something which we can code up and make repeatable and put into our stack. And so we want to be able to take that kind of circuit and divide it into pieces, into a discrete set of instructions that then we can use to compile any circuit. And so for this, we developed this framework of logical blocks. So it's a way of really being explicit about a sequence of operations that you can make in these topological codes. And so we can go from this sort of kind of abstract picture on the left to a very definitive representation of those blocks, where they look like these cell complex representations defining the topological features. So we now can make it really explicit. This is the kind of instruction that we can and do write in code. And it also enables you to start to simulate these gates, simulate circuits, look at the behavior of the way the changes in structure affect the behavior of the logical gates. Okay, so I just want to pause at this point and kind of comment that everything until this point that I've talked about has been completely platform independent. So the way you do logic, the way you compile these gates, this could be the same for any hardware which is using kind of an underlying fault-tolerant hardware underneath. And so these things are all portable between platforms. And now I'm going to move on to the bit where we're really looking at what is happening with the photons. How do we get to create this kind of fault-tolerant logic using our photonic hardware? And so for that, we need to look at how do we actually create these logical blocks? How are we going to make them out of our photonic operations? And so we're building on an architecture based on fusion-based quantum computation. So this is from some work that we put out last year, looking really at a very natural way of building up to error correction using photons. And so what happens here is that we create some entangled photonic states. So they're relatively small, constant-sized photonic states. And then we create a whole number of them, and we arrange them in this 3D construction that we call a fusion network. And it's kind of being arranged on those logical blocks, those logical gates we want to implement. And then to connect those states together, we can perform these projective entangling measurements, also a very natural operation with photons, that projects those things into an entangled state and extracts classical information. And so by doing this, if you arrange this in the right way, you get error correction, you get classical data which has redundancy in, and which is giving you the outcome of the logical gates you wanted to run. And so finally, we need to take this and actually map it into a hardware architecture. And so for this, we have a modular architecture. So at the high level, it's an array of modules connected together by optical fiber. And inside those modules is a generator that is producing these entangled states. It routes the photons to different locations where they go into fusion gates, where the photons get measured. And it's at those fusions where we're detecting them that we're able to actually interact with them and be implementing an algorithm. So this architecture we call the interleaving architecture because it's making use of kind of time delays in optical fiber. And so just zooming in one more level, of course, the critical thing we want to know is how is our algorithm actually mapping down through all these layers and we're implementing it at the level of hardware. And this is where that's happening ultimately. So inside these fusion measurements, these are reconfigurable. And the reconfigurability allows us to interact or measure the photons in different ways, and by doing so, change the logical operations that we're doing. And so inside that, if we really look at what's going on in the hardware, ultimately this comes down to optical switches. So inside those fusion devices are waveguides, and they have phase shifters on them in certain locations, and by applying a voltage, we're able to adjust the refractive index of the material and apply a phase that we control onto the photon. And so this is sort of the bottom of the stack, gone all the way down, started at some circuit describing a quantum algorithm. You kind of go through these layers of instructions, and then ultimately we're getting down to hardware where we're just applying a voltage to execute these operations. So, okay, this was a very quick run through of this stack. Gone through all these different pieces, and I think hopefully, not to really go into detail, just to give a high-level picture of how this fits together. And I think over the last few years, we've spent a lot of time really understanding this stack, building up, code, languages, ways of defining these instruction sets so we can be explicit about it and look at the way it behaves and analyze resource counts and understand its behavior. And that puts us in a position now where we can start to look at it as a whole and see the places where there are opportunities for improvement. And there's still a lot of things that need to be evolved and improved and worked on in this architecture to really get it to the point where it's truly scalable. So I just want to look at three new results to just give you some kind of ideas of the kinds of things we're working on and the kinds of places where there are improvements to be made. So these top two recent publications there are on the archive, so you can take a look at them, and the last one is something that is going to be coming out soon, so I'll just give you a bit of a preview. So I want to start talking about this active volume architecture. So this is something where, when we're looking at this stack, I showed you a very basic version of this logical architecture with a linear register of logical qubits and only local connections between them, so nearest neighbor. And one of the things that we've kind of thought for a long time about photons is it's incredibly flexible. Once you've got a photon in an optical fiber, it's really no extra cost to connect things non-locally or in different ways. And so surely this should be something that we can exploit to benefit the architecture in some way. And so this was the kind of origin of the active volume architecture work, where we're looking at these quantum circuits, logical quantum circuits. If you look at those circuits, you really see that a lot of the time, the logical qubits are doing something essentially trivial. So they're maybe sitting there just waiting to undergo a gate in a future time step. Or maybe they're being used to connect things together that were far apart, so they're kind of moving things in space. So this picture at the top showing you a circuit where a lot of the volume of that circuit is actually doing something trivial. And the picture at the bottom showing you a kind of topological version of this picture, what it looks like as a circuit, showing the same thing, where a lot of the volume is essentially wasted. But the thing is, it's really real volume, like you're creating it, we're creating resource states, we have to decode it, it takes real time and energy. And so we'd really like to be able to just eliminate that volume from circuits. And it really can be a very large fraction of the circuits, up to sort of 99% even in some cases of the circuits is this space that's really doing nothing computationally useful. And the result of this paper, which is showing that actually by using optical fiber, by slightly changing what's going on inside these interleaving modules and adding some non-local connections that connect different locations, we can actually build these circuits in different ways that really does allow you to eliminate almost all of that inactive volume, and that can reduce the runtime of algorithms by as much as 50x in some cases. So this is nice. It really shows us that there are ways of exploiting these properties of photonic connections, and yeah, hopefully there's more things to be found in this direction. Okay, so next, lower overhead magic state preparation. So magic states are a really fundamental part of fault-tolerant architecture. We've got to prepare them to be able to do non-Clifford operations. But the problem is they're really expensive. It takes a lot to prepare them, and that cost is really dependent on the quality of the states that you put in. So if those states are cleaner, then you can really reduce what it costs to do the rest of the preparation. And so in this work, also recently on the archive, some people in the team found ways of doing much better post-selection of those states that you're putting in, so really exploiting as much of the information as possible that you're getting from syndromes in the error correction, and that can massively reduce the overhead of preparing those initial states of a certain quality. So, magic state injection is one of these things that just repeats over and over again during a fault-tolerant algorithm, and so this can hopefully have a big impact. And then finally, just talk a bit about error correction itself. So for photonics, optical loss is kind of enemy number one. It's the big challenge of optical circuits. You really need to be able to tolerate the fact that photons just will get absorbed into the devices and into the hardware. And we have our previously kind of best published architecture in this paper on fusion-based quantum computation had a protocol that could tolerate 2.7% optical loss on every single photon. So every photon of every resource state can tolerate 2.7% loss. And we have now got new, more advanced protocols that can push that number up to 7.5%. So it's kind of almost a 3x improvement on those previous things. So this is going to be kind of appearing soon, so keep an eye out for it. But yeah, this is kind of really exciting, really makes it, brings the requirements on the hardware to somewhere that's more achievable. So yeah, I think just to wrap up, I think quantum architecture as a whole field and of what we've been doing at PsiQuantum has, over the last years, really been getting to the point of having a complete picture of that architecture, building up the knowledge of how you define instruction sets, how you piece these things together to build up a whole fault-tolerant stack all the way from algorithms down to hardware. And now we're at the point of being able to iterate and improve and advance on that. And I think some of these results showing that we really can start to exploit some of the unique properties of photons and use them to our advantage in the architecture. So these are some things, and I'm pretty hopeful that there'll be more things like this that we'll be able to find in the coming months and years. So thanks very much for your attention.
All right, thank you very much. And since this was the last one of the session, our coffee break is now, and we have time for plenty of questions if we have any.
Thank you for the very nice talk. For the loss tolerance, do you think it's the best you can do, or are you working to increase that further, or do you think it's enough for the architecture you have?
You're talking about the loss thresholds. Yeah, great question. So I am very optimistic that that can be pushed further. And I think the thing is that even when the hardware components are below the threshold, it's still hugely advantageous to push those numbers up. So once you're below the threshold, then it's all about footprint. But that's also going to be a hugely important factor of scaling up to large devices. So yeah, absolutely trying to push that number up, and I'm optimistic about it.